Hello, and welcome to this brief presentation related to SI units. This presentation outlines a brief introduction to this unit system.
And here's a brief overview of the contents of the SI units presentation. We commence with an introduction, essentially a case study of the importance of all engineers working to the same unit system. Then we state the SI base units, of which there are 7. We consider SI supplementary units. And then we state an array of SI derived units. And exercise 1 is essentially a table which we need to complete and helps illustrate how derived units are formed from the base units. Next we have SI prefixes, introduction to the use of prefixes, some examples related to common engineering properties. This section includes exercise 2, but highlights that we should not use double prefixing within the SI units. Next we consider some non-SI units, for example the ton, the litre, the bar. These are units engineers often use but are not actually part of the SI unit system. Then we consider Greek symbols, the Greek alphabet, symbols of which we often use within calculations or engineering technical reports. Typical examples shown here. Then we return to prefix usage. Part 1 contains an exercise 3, and prefix usage part 2, exercise 4. Both considering various aspects of prefix usage. We conclude with a very brief overview of other systems of units, although of course within our engineering technician studies we must always use SI units. And here are the approximate start times related to the various sections contained within the presentation, hopefully to aid your ease of access through the presentation, but please note all times are generally rounded to the nearest minute.
Let's initially set the scene and try and explain why engineers should all use the same system of units, and preferably the SI system of units. So as an introduction to unit systems, I've got this illustration here related to the Mars orbiter that was lost due to a mix-up between imperial and metric units. This is extracted from a newspaper article from 1999. So in a space race, the search for signs of water is vital for knowing whether life ever existed or can exist on Mars. 2 teams of engineers were involved with building this particular probe. One team was working at NASA's Jet Propulsion Laboratory in California, and the second was space firm Lockheed Martin in Colorado. According to a preliminary report, Lockheed Martin gave the acceleration data in imperial units of pounds force, instead of the metric equivalent in newtons. At NASA, the numbers were entered into the computer, which assumed metric measurements. The NASA chief engineer said, in our previous Mars missions, we have always used metric units. At first, after the launch of the probe, the effect of this confusion over unit systems was so small it went unnoticed. But due to the discrepancies between the systems, as the marathon journey progressed, it ended up in disaster, with the probe actually crashing onto the surface of Mars instead of orbiting the surface of Mars. Essentially, all because unit inconsistency. So the point I'm trying to make here is it's very important that we use a defined system of units within our engineering calculations. Let's consider SI base units. Engineers can be exposed to various systems of units, but the system I'm going to refer to here is the one we should be using throughout our studies, and that's the International System of Units, the SI system, Systeme International.
Here's a general note related to the expression the SI system. Technically speaking, the expression SI system is non-preferable because it contains a redundancy, as SI stands for Systeme International d'Unité, which translates to the International System of Units. Thus, stating the SI system is essentially saying the International System. and thus the redundancy. However, in practice the expression SI system is widely used and understood, especially in informal situations or in teaching environments. Here's an extract from one of my textbooks when I was an engineering student. And this book clearly refers to the SI system within its content. However, within academic or professional writing, it is preferable to state SI units or SI or the International System of Units. So often throughout the presentation you will hear me refer to the SI system, but I've stated here that's not technically correct. And also as a minor point, you will see me place dots between the S and the I, but again, technically speaking, we do not need these dots. We simply can write SI without the dots. So I hope these slight discrepancies do not detract from your understanding of this presentation, which tries to outline to you the main elements of the International System of Units.
So in the SI system of units, there are 7 what are termed base units or primary standards, and they're listed in the table below. So the first quantity is length, and in the SI system that's the meter, symbol M. Second quantity is mass, that's the kilogram, symbol lowercase kg. Third quantity is time, and that's the second, symbol S. For electrical work, fourth quantity is the electric current, and that's the ampere, symbol capital A. Fifth quantity is temperature, which in the SI system is the Kelvin, symbol capital K. And then the sixth quantity is luminous intensity, the candela, symbol CD. And the seventh is the amount of substance, which is the mole, designated as MOL. So those are our 7 base units. In the work we're going to cover, our level of study, we will certainly see the first, second and third units, but we will see electric current, temperature and luminous intensity within certain aspects of our engineering studies. Supplementary units. There are actually supplementary units to these 7 base units. These 2 supplementary units are dimensionless units and are the radian and the steeradian. The radian, denoted RAD, is the unit of plane angular measure. We're quite familiar at this level of study with a degree, 360 degrees in a circle, but that's an arbitrary unit of measure, whereas the radian is a pure mathematical unit of measure and based on a geometrical construction. So the radian is the angle subtended, angle shown here, between 2 radii, shown here, when the arc of our sector is 1 radius in length. So when the arc length here is equivalent to the radius of the sector, we have 1 radian. From a previous presentation related to radian measure, we know there are 2 pi radians in a circle, so 2 pi radians equivalent to 360 degrees. So therefore 1 radian is 360 degrees divided by 2 pi. So 57.2958 degrees to 4 decimal places. That's just for reference. So very crudely speaking, you can consider 1 radian to be approximately 60 degrees. That's very crude, but it gives you a feel for the conversions between radians and degrees. So if I'm given 2 radians, for example, I know I've got, nominally speaking, 120 degrees. Just a useful ballpark figure when you're converting between radians and degrees. The second supplementary unit is the steeradian, denoted SR. This relates to a solid angle equal to the solid angle that encloses a surface on a sphere that is equal to the square of the radius of the sphere. For a general sphere, a radius r, a portion of the surface area, A, is equal to r squared. So when the surface area of an object is equal to the square of the radius, then the solid angle subtended is 1 steeradian at its centre. Let's consider SI derived units. Exercise 1. For each of the quantities listed in the table below, we've got to add the correct unit from the list of SI units stated here. So for the first quantity, area, symbol capital A, the unit would be the meter squared. So that's the meter squared here. If we consider the quantity of mass is a base unit in the SI system, have a unit of the kilogram. And that's symbol lowercase kg. Volume would be meters cubed. Think of working out the volume of a rectangular prism. It will be the base times the height times the length, so that would be meters cubed. Symbol m cubed. Time in the SI system, where time is a base unit, again we know that's a second. Symbol lowercase s. Now the SI system is what is termed a coherent system. So we can find the units of a particular quantity if we know the formula it's derived from, or if we know an appropriate law. For example, Newton's laws of motion help us to find the unit of force, you'll see later on. So now we're considering the quantity of density. Density is defined as mass divided by volume. We know from above that mass is in kilograms, and we know that volume is in meters cubed. So the unit of density is kilograms per meter cubed. Written as kilograms per meter cubed, or the kilogram per meter cubed can be written as kilograms meters to the -3. That's using the reciprocal rule of indices. So be aware of that, because in lots of engineering literature, the negative index is used on various units. So kilograms per meter cubed is the same as kilograms meters to the -3. It's the same unit. Exercise 1 continued. Some further quantities here. Linear velocity is defined as distance travelled divided by time taken. So symbol V for linear velocity. The unit would be distance is in meters and time is in seconds. So the unit for velocity is meters per second. Symbol for the unit is meters per second. Or we could write that as meters second to the -1. Again, using this negative index principle. Linear acceleration is defined as the velocity divided by time. We know velocity is meters per second. Divide that by time. Then the unit for linear acceleration is meters per second squared. Symbol meters per second squared. Or again, meters second to the -2. Gravitational acceleration, that's a specific acceleration, that's vertically downwards. So that has the same unit as the linear acceleration. It's just a specific acceleration. It's 9.81 meters per second squared acting vertically downwards. So same unit as linear acceleration. Now force is defined as mass multiplied by acceleration. That's actually Newton's second law. So force, symbol F, or sometimes P, is used for pull or push. So the unit of force would be mass in kilograms multiplied by acceleration in meters per second squared. So a kilogram meter per second squared, or kilogram meter seconds to -2, would be the unit of force in the SI system. However, you will very seldom see the unit of force stated as kilogram meters per second squared, because certain units in the SI system are given names related to eminent figures that were involved with research and work associated with that particular quantity. So in this particular case, we term the kilogram meter per second squared as a Newton, after Sir Isaac Newton. And that would be symbol N. So forces in the SI system are actually stated in newtons, but in terms of their base units, a Newton is a kilogram meter per second squared. The next quantity, weight, is a specific force. It's a force that acts vertically downwards, and weight is defined as mass times gravitational acceleration. So it will have the same unit as force above. So we measure weights in terms of newtons. Potential energy is given for us here. Potential energy is defined as the Newton meter, Newton multiplied by meters here. And again, a name is given to this derived unit of the Newton meter. We often call that the joule, giving credit to people that worked in this area of study. So the SI unit of potential energy can be stated as Newton meters or the joule. And often the joule is the unit that's used when calculating various energies. Our next quantity is power. It's defined as energy divided by time. Now above, we've stated that the energy is in Newton meters or joules. So power could be written as joules per second. That's the energy divided by the time in seconds. But again, as you probably know, we have a name for the joule per second, and that's the watt. So power is in terms of watts. Pressure is defined as force divided by area. We know above that force is in newtons. Area would be meters squared in the SI system, so the unit of pressure is the newton per meter squared. So in symbol form, newton per meter squared, or again, that could be written as newton meter to the negative 2. Now the quantity stress has the same formula as pressure. Pressure and stress are related. They're different quantities. Pressure often induces a stress, but the unit of pressure and stress are the same. So newtons per meter squared. I'll let you now consider the remaining quantities in the table. Torque and moment, which notice have the same formula here. Angular displacement, angular velocity, and angular acceleration. We're given that the unit of angular displacement is the radian, so I'll let you see if you can derive the unit for angular velocity and angular acceleration from that. So I'll leave you with these last few boxes to complete on your own. I'll show you the answers on the following slide.
So here's exercise 1, commencement of the answers. This table shows the headings of quantity, the typical symbol for the quantity, the unit of the quantity, and the symbol for the unit. I'll let you review the contents of the table at your own pace, but there are a few points I'd like to highlight related to the convention of using SI units. On the previous slide, when I derived the unit for area, I actually stated it as meters squared, but with the strict SI convention, the unit stated in any technical document should actually be the meter squared. In other words, I used the plural when I was defining the unit to you, but in a document I actually should use the singular term. The same relates to volume. I defined it previously as meters cubed, but the SI convention states it is the meter cubed. So just clarifying this SI convention, in everyday usage, plural units are often stated. However, in formal documents and reports, singular units are stated. So in formal scientific or technical writing, the singular form of a unit is preferred. For example, the official SI unit of velocity is the meter per second, shown in two different symbol forms here, and that is stated as a singular meter per second. Everyday and informal usage, within speech and less formal writing, the expression for the unit of velocity is often stated in meters per second, i.e. the plural. This is especially when referring to a specific value of velocity. For example, the car was travelling at 15 meters per second. We use the plural in such statements. So I hope that clarifies the SI convention in this instance. Another SI convention to be aware of is, for example, the unit of force, which we know has the unit of the kilogram meter per second squared, but we've given that a special name. We refer to it as the Newton. But the SI convention states when we write the word Newton in formal reports, we actually write it with a lowercase n. However, the actual symbol used for the unit of the Newton is uppercase N. So again, be aware of this convention. And a general note from my perspective, students studying engineering, even after many months of study, they still confuse mass and weight. They often state that weight is in kilograms, which of course is not true. The quantity mass has the SI unit of the kilogram, but weight is actually a force. It has the same unit as force, which is the Newton. So do try and be aware of that, because as I say, that's something I've noticed students often confuse mass and weight. And it's understandable, because when you converse with engineers, they often conflate mass and weight. I've seen specifications that state weight in terms of kilograms or even tons, both of which are actually mass units in the SI.
I do sometimes find students, even after many months of study, of engineering science, engineering mechanical principles, etc., still refer to the unit of weight as the kilogram, which is incorrect. So it's very important to note in the SI system, weight has the unit of the Newton. If it helps, refer to weight as weight force, because forces in the SI system are always measured in newtons. So forces in general can be applied in any direction, but a weight force specifically acts vertically downwards, as we can designate with an arrow, because weight force is a vector property. In exercise 1, answers continued. Again, notice for the quantity of potential energy has the unit of Newton meter. When we write the Newton meter, it's lowercase n. This is derived units given a special name, and we call the Newton meter a joule. Again, notice when we write the joule, it's lowercase. When we use the symbol for joule, it's uppercase. Power has a unit of the joule per second. And again, this derived unit is given a name. We call it the watt. Lowercase w when we write the word watt, but uppercase w when we write the symbol for watt. Pressure is another derived unit. From the formula of force divided by area, it will be Newton per meter squared. And again, we can refer to pressure in terms of Pascal. So another derived unit is given a name. Again, lowercase p when we write the Pascal, but uppercase p when we write the symbol for pascals, which is PA. The unit of stress, same as the unit of pressure. Notice we use the Greek symbol lowercase sigma to denote stress. So same unit as for pressure, it's Newton per meter squared. Although the term is usually associated with pressure, I have seen various companies use the Pascal for units of stress. Quantity torque is defined as force multiplied by distance. So in the SI system, force is in newtons, distance in meters. So the Newton meter is the unit of torque, capital N when we write Newton meter. And the same for moment. Moment and torque are related, but slightly different concepts. And the final quantities here, angular displacement, often stated in terms of Greek symbol theta, is the unit of the radian, the supplementary unit. Angular velocity, which is the angular displacement divided by time, usually denoted by lowercase omega, is the radian per second. And finally, angular acceleration, which is angular velocity divided by time, and often stated as the Greek symbol lowercase alpha, is the radian per second squared. So that's a listing of the various derived units, most of which we will encounter in our engineering science and our mechanical principles studies. Let's consider SI prefixes, and the ones we'll use predominantly will be kilo, mega, the giga, the tera, and also the milli, the micro, the nano, the pico. Within the SI system, we often use standard numerical prefixes as shown in the table here. These standard prefixes are used for multiples and submultiples of units in the SI system. And the table shows preferred prefixes, which are multiples of 10 to the power of 3. For mechanical engineering, salient prefixes used will be kilo, lowercase k, that has a value of 10 to the power of 3, in other words, multiplying by 1,000. The mega, capital M, that's a value of 10 to the power of 6, so that's like multiplying by a million. Giga, capital G, that's equivalent to 10 to the power of 9, so that's like multiplying by a billion. And we'll also often see milli used, lowercase m, that's 10 to the negative 3, so that's like multiplying by 0.001. And micro, Greek symbol here, we'll mention later on, that's equivalent to 10 to the negative 6, so that's like multiplying by 0.000001. Within electrical engineering, you may sometimes see the tera used, capital T, that's multiplying by a trillion here. And also nano, lowercase n, that's like multiplying by 10 to the negative 9, shown here. And pico, lowercase p, like multiplying by 10 to the negative 12. multiplying factor shown here. There are further prefixes which extend a numerical range, but that encapsulates all the ones that we will see within the work we're going to consider. There are other prefixes such as hecto, deca, deci and centi. Often you'll see centimetres used, even within standards, but those are classified as non-preferred prefixes. Preferred prefixes are always a multiple of 3, so 10 cubed, 10 to the 6, 10 to the 9, 10 to the 12, or 10 to the negative 3, 10 to the negative 6, 10 to the negative 9, 10 to the negative 12. Those are the preferred prefixes we should use. Just notice this column here, which relates to the exponent use on a calculator, sometimes shown as an EXP key. On a calculator, for putting in powers of 10, there's usually a special key that we can use for convenience. The next slide illustrates this. So here's two scientific calculators. These are calculators I use. What you notice is both have the EXP key shown here and shown here. What this key allows us to do is to insert the powers of 10 very quickly, and I would strongly encourage you to get used to using this button if you're not already familiar with it, as opposed to raising 10 to the power of. Extra keystrokes are required, and this exponent key is used specifically for inputting powers of 10. So for example, if you wanted to insert the value of 2.5 times 10 to the power of 6 into the calculator, all I would type on my calculator is 2.5. I would then press the EXP key, the exponent key, written as E in handwritten calculations, and simply enter 6 after the exponent key. And that multiplies 2.5 by 10 to the power of 6. And with the SI system, because we often have very large numbers, or very small numbers, very quick and easy way of inserting powers of 10. Just for reference, on some more modern calculators, the EXP key is actually replaced with the specific times 10 to the X key, which of course means exactly the same thing. So if I wanted to enter the number 3.6 times 10 to the power of 9, I would simply enter 3.6, press my times 10 to the X key, and enter 9. And that will multiply 3.6 by 10 to the power of 9. So whichever format your calculator has, I would encourage you to use the exponent key for entering powers of 10. So that's why in this column I've shown the E notation. So for example, referring back to the kilo prefix, which is times 10 to the power of 3, that would simply be E3 on my calculator, the exponent key, and then 3. Mega would be E6, milli would be e to the negative 3, micro would be e to the negative 6, and so it goes on.
And just note this typographical error on this slide. This should state exponent format, not exponential format. And if it helps, here's a slide stating how to use the exponent or powers of 10 key on your calculator. Given the example here, we're asked to enter the microstrain value of 4,200 microstrain. Notice that the micro is the prefix, so this is 4,200 times 10 to the negative 6 strain. So if we were typing this into our calculator, we enter the mantissa, the main part of the number, 4,200. Then we press the EXP, or 10 to the power of X key, which indicates the exponent is being entered. Then we enter the exponent, so we type in the power of 10 required, in this case that's a 6. And then we use this key on our calculator, so if the exponent is negative, we use the plus or minus or the sign change key to adjust the number, make it negative. So we type in 4,200 EXP negative 6.
On this slide, I've tried to show some examples of prefix usage for typical engineering values. So for example, a material elastic modulus, this is actually for steel, is 210 000 000 newtons per meter squared. Now quite obviously engineers would not want to write that particular value down. This is where prefixes are really useful. So we could write this elastic modulus value as 210 multiplied by 10 to the power of 9. So in other words, considering my decimal point is here, I move it 1, 2, 3, 4, 5, 6, 7, 8, 9 places, and I can write it as 210 multiplied by 10 to the power of 9. And the unit would be newtons per meter squared in this case. And what we can do using the SI prefix is to replace the times 10 to the 9 with the symbol G, which is the giga symbol. So 210 times 10 to the 9 newtons per meter squared is the same numerical value as 210 giganewtons per meter squared. And again, back to the input on the calculator, that would be inputted as 210 exp 9. Next quantity here, we've got a bending stress level, and a beam, for example, is 124 million newtons per meter squared. So again, we could write that as 124 times 10 to the 6 newtons per meter squared. Again, considering my decimal point is initially here, you move it 1, 2, 3, 4, 5, 6 to the left, and I can write it as the 124 times 10 to the 6 newtons per meter squared. But again, if I want to, I can use an SI prefix. The times 10 to the 6 can be replaced by symbol M for mega. So 124 times 10 to the 6 newtons per meter squared is the same value as 124 meganewtons per meter squared. And again, entering that on my calculator, that will be 124 exp 6. Next quantity is atmospheric pressure. It's given as 101,000 pascals. And we could write that as 101 times 10 to the 3 pascals. Again, considering the decimal point initially here, we'd move it 1, 2, 3 places to here. So that's where the 101 times 10 to the 3 is derived from. But again, using the appropriate prefix, the times 10 to the 3 can be written as the kilo prefix, lowercase k here. So 101 times 10 to the 3 pascals is the same as 101 kilopascals. And again, on my calculator, I would enter that as 101 exp3. And an applied force or applied load, often force and load are interchangeable terms, of 10,000 newtons could be written as 10 times 10 to the 3 newtons, or of course we could replace again the 10 to the 3 here with the kilo prefix. Just a different unit here. Examples of SI prefixes continued here. We've got a geometrical dimension here of 1.3 millimeters. So in this particular case, we're actually given a prefix. This first M is the prefix, the second M is the unit. So don't forget that milli is times 10 to the negative 3. So we could write the 1.3 millimeters as 1.3 times 10 to the negative 3 meters. And that has a numerical value of 0.0013 meters. Of course, on my calculator, I would write that in as 1.3 exp negative 3 meters. So this times 10 to negative 3 becomes the exp negative 3. We're given a material strain value of 0.0042. Now within engineering, for metallic materials, we often write strains in terms of microstrain, in other words 10 to the negative 6. So in this particular case, I'm moving the decimal point from here, 1, 2, 3, 4, 5, 6. That will then give me 4,200 times 10 to the negative 6 strain. So the 4,200 times 10 to the negative 6 strain could be written as 4,200 microstrain, where the micro is a 10 to the negative 6. Of course, on my calculator, entering that value, I'd write 4,200 exp negative 6. If we consider a nanotube using nanotechnology, has a diameter of 0.000000067 meters, we could write that as 67 times 10 to the negative 9 meters.
In other words, moving the decimal point
1, 2, 3, 4, 5, 6, 7, 8, 9 places to the right, we could write this as 67 times 10 to the negative 9 meters. Inserting a suitable prefix, the times 10 to the negative 9 is actually nano. So we could write it as 67 nanometers, or entering on my calculator 67 exp negative 9 meters. A copper wire has a resistivity of 0.000 0.0000172 meters. Moving the decimal point 1, 2, 3, 4, 5, 6, 7, 8, 9 places to the right, we could write that as 17.2 times 10 to the negative 9 meters. If we want to insert a prefix, then 10 to the negative 9 is actually the nano prefix again. On our calculators, we'd enter that as 17.2 exp negative 9 meters here. And finally, we're given a capacitor has a capacitance of 0.00000000002 farads. If we move the decimal point 12 places to the right, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, we could write this value as 200 times 10 to the negative 12 farads. And using a prefix, we could replace the times 10 to the negative 12 with pico. So 200 picofarads would be the same value. On my calculator, I would type the value in as 200 exp negative 12 farads. So that's just some examples of how we can use prefixes to express very large or very small numbers. I would strongly encourage you to engage with prefix usage because engineers and textbooks, etc., use prefix usage extensively within a wide array of quantities. An important point to note is that multiple prefixes in the SI system should not be used. So, for example, 32 megamillimeters has a double prefix. The capital M means 10 to the 6, and the lowercase m is the milli prefix, and that means times 10 to the negative 3. So from the first law of indices, 10 to the 6 multiplied by 10 to the negative 3 becomes 10 to the 3. And 10 to the 3 in the SI system is the kilo prefix K. So in other words, 32 megamillimeters is not allowed, but that can be simplified to 32 kilometers. Exercise 2 for you to have a quick review of. We're given in the question 2.3 mega kilowatts. What would be the preferred SI format for that quantity? The answer is shown on the following slide. So exercise 2, we need to rewrite the double prefixed 2.3 mega kilowatts with a single prefix. So noting that capital M mega is times 10 to the 6, lowercase k for kilo is times 10 to the 3, and then for the first law of indices, 10 to the 6 multiplied by 10 to the 3 is 10 to the 9, and in the SI system, that's the giga prefix. So 2.3 mega kilowatts should be written as 2.3 gigawatts. So be careful to avoid double prefixing in the SI system. Let's outline some non-SI units that are acceptable to use within the SI system. For reference, there are non-SI quantities that are in common use and that we're allowed to use within the SI system. So you'll see within general use these non-SI units used. For example, loads or forces applied to structures may be stated in kilogram force or tons, both of which must be considered as masses within the SI system. Pressures are sometimes stated in terms of bars or millibars, in the weather forecast for example, and although the bar is not an SI unit because 1 bar is approximately atmospheric pressure, it's a very useful unit and engineers often do refer to it. And of course volume, often stated in litres, you buy petrol for example, when you buy milk etc. Here's a list of the non-SI units in common usage. So quantity here, mass is the metric ton. There is actually an imperial ton, that's from the imperial system. Abbreviation is usually lowercase t, and 1 ton is equivalent to 1,000 kilograms. You must be aware of that. The electrical energy, there's the kilowatt hours often used. Electricity bills you pay in terms of kilowatt hours. And 1 kilowatt hour is the same as 3.6 megajoules. Atmospheric pressure, already mentioned, is the bar, symbol lowercase b. And 1 bar is 100,000 newtons per meter squared, or 100,000 pascals. Length, we've mentioned this as well previously, can be used in terms of the micron and micrometers, and 1 micrometer is 1 times 10 to the negative 6 meters. And we just mentioned the volume can be in litres, lowercase l, and 1 litre is 0.001 meters cubed. In other words, there are 1,000 litres in a meter cubed. So that's worth remembering. 1 meter cubed is equivalent to 1,000 litres. Also, just note for reference that 1 tonne can be expressed as 1 megagram, and of course both are equivalent to 1,000 kilograms. So 1 tonne or 1 megagram is 1,000 kilograms. Let's review some of the commonly used Greek symbols. Let's briefly review the Greek alphabet. Within engineering, you'll find that lots of equations, lots of formulae often include Greek symbols. So when we run out of our own symbols from our own English alphabet, we then use the Greek alphabet. So on this slide, on the next slide, I've outlined the full Greek alphabet. The left-hand column here I have the name of the Greek letter, its uppercase and lowercase designation in the next 2 columns. And on the right-hand side, I've had what I've called my student speak column. And these are just descriptions that past students have used to try and remember the various Greek letters. I would just highlight here some of the more common Greek letters that are often used within mechanical and electrical engineering. So alpha and lowercase alpha is often used in things like thermoconductivity, specifying angles, and in student speak, that was known as the fish. Second Greek letter is beta, lowercase beta, often used for angles, and that was referred to by the students as the tall curly bee. Gamma, lowercase gamma here, used for angles or volumetric expansion. That was known as curly y to the students. Delta, both uppercase and lowercase delta are commonly used. Uppercase delta often means change in a quantity, change in a volume, change in energy. And lowercase delta used for expansions, deflections, sometimes angles. Students speak, that was the tadpole. Epsilon, lowercase epsilon, to use for strain in mechanical engineering. Students refer to that as the backward 3. Zeta, lowercase zeta, sometimes used for damping coefficient, damping constant, used in the Laplace transforms. Eta, lowercase eta, sometimes relates to efficiency of systems. Students refer to that as the swan's head. Theta, lowercase theta, often used for angles or for temperature. Students remember that as a 0 cut in half. Lambda, lowercase lambda, sometimes used for spring stiffness. It's like a tent with an aerial, as one student said. Mu, lowercase mu, used for friction coefficients. Students call that a tall U. And nu, lowercase nu, sometimes used for Poisson's ratio. An italic V was a student's description of that letter. The Greek alphabet continued. Further symbols used in mathematics engineering. Pi, uppercase and lowercase pi. Students refer to that as a stool. Rho, lowercase rho, often used for mass density. Students refer to that as a curly p. Sigma, both uppercase and lowercase sigma are used in engineering, maths and science. Uppercase sigma often used as shorthand notation for summate a column of numbers, for example, against standard deviation. Lowercase sigma used for axial stresses, bending stresses in beams, and also used for relative density in fluid mechanics. In student speak, lowercase sigma was a sideways 6.
Tau, lowercase tau,
often used for torsional shear stress. Curly T was a student's description. And omega, both uppercase and lowercase omega, used in engineering. Uppercase omega used to denote the unit of the ohm in electrical resistance. Lowercase omega often used in mechanical engineering for angular velocity, or in beam analysis for uniformly distributed loads. And for lowercase omega, the students described it as a curvy W. Let's consider an exercise related to prefix usage. Here are examples of SI base units and their subunits. If we're asked to convert 3 millimeters into its SI base unit, the meter, we note that the prefix is the M in the above expression here, and we know that M signifies milli, and milli corresponds to 10 to the negative 3 as a numerical value. So 3 millimeters is actually 3 multiplied by 10 to the negative 3 for the millimeters. So moving a decimal point 3 places to the left, 3 millimeters is actually 0.003 meters. So that's a typical example of what we're going to review in the next exercise. So in exercise 3, we're asked to remove the SI prefix from each of the quantities given and then state the actual numerical value. So for example, we've got 4 millimeters. We've got to write that in terms of the base unit, so that'll be meters. So the 4 millimeters, the milli is the prefix. Don't forget that milli is 10 to the negative 3, so we could actually write that as 4 multiplied by 10 to the negative 3, or moving a decimal point 3 places to the left, that will be 0.004 meters. So part B, we're given 8.1 centimeters. So here the prefix is the centi. It's actually a non-preferred prefix. Centi is 10 to the negative 2. So we could write that as 8.1 multiplied by 10 to the negative 2. Moving a decimal point 2 places to the left here. That's a value of 0.081 meters. Part C, 6.1 millijoules. Again, this is the milli prefix. So that's 10 to the negative 3. So 6.4 times 10 to the negative 3. Units are joules. So that's equal to 0.0064. And part D here, we've got 14 kilovolts. The lowercase k there, that's the prefix for kilo, and that's 10 to the power of 3. So we've got 14 times 10 to the power of 3 volts. Moving a decimal point 3 places to the right now, that becomes 14,000 volts. So try and be aware of the difference between the prefix and the unit. In part A, the prefix was the milli, that's the 10 to the negative 3, but the unit was the meter. So our answers are stated in terms of meters. In part 2, the prefix was centi. That was the 10 to the negative 2. Again, our unit was the meter, so our answers are stated in meters. Part C, again, prefix is a milli, so 10 to the negative 3. The unit this time was the joule, so the answers are stated in joules. In part D, the prefix was the kilo, that's 10 to the positive 3, and the unit was the volt, so our answer is stated in volts. So try and differentiate between prefixes and units. Exercise 3 continued. Again, we're asked to remove the SI prefix and state the quantities in their actual values. I would encourage you to start the presentation and attempt this exercise. Just note the negative index notation that is used within some of the questions. As I said before, that just means 2.5 kilometers per second, and in this case that's 25 kilometers per second squared with a negative 2. But that doesn't affect the prefix. So again, distinguish between the prefix and the unit. In part E, the prefix is the kilo, the ohm is the unit. Part F, the prefix is the kilo, the unit is the meter per second. In part H, the prefix is the micro, the unit is the farad. Part I, the prefix is the milli, the unit is a henry. Part J, the prefix is the milli, the unit is the meter per second, and so it goes on. Just be careful with part P, where we have 2.4 millimeters squared. That actually means 2.4 and the millimeters is all squared. So the prefix here is the milli and the unit is the meter, but they're both squared. I'll let you think about that when you come to answer part P. I'll encourage you to start the presentation and attempt exercise 3. Exercise 3, here are the answers. I'll let you review them at your own pace. Exercise 3, here are the answers, continued. Just note part N here. We have 72 kilonewton millimeters. Be careful here, there are two prefixes. The kilo is a prefix, times 10 to the 3, but also the milli is a prefix, times 10 to the negative 3. The unit here is the Newton meter. We can see from the calculation here the 10 to the 3 multiplied by 10 to the negative 3 cancel each other out. So the answer is 72 Newton meters. So 72 kilonewton millimeters is the same as 72 Newton meters. In part O here we have megagrams. The prefix here is the mega. Now mega is actually times 10 to the 6. So we could write 12.1 megagrams as 12.1 times 10 to the 6 grams. We need to be careful here because the base unit in the SI system is the kilogram. There's actually a prefix on the base unit. So 12.1 megagrams should really be written as 12,100 kilograms. Just be aware in part P, we said before, that is actually 2.4 millimeters all squared. So the prefix is the milli, and the milli is squared. The unit is the meter, and the meter is squared. So 10 to the negative 3 all squared, using the third law of indices, that becomes 10 to the negative 6 meter squared. Moving the decimal place, 6 places to the left, the actual value is 0.0000024 meter squared. Here's a further exercise related to prefix usage. Exercise 4. We're asked to express the following quantities in a more concise SI format, using an appropriate prefix. So, part Q here, 7,000 meters could be expressed as 7 kilometers. If we move the decimal point, 1, 2, 3 to the left, that would be 7 times 10 to the 3 meters, or using a prefix, 7 kilometers. Next question, 12,000 kilograms. If we move the decimal point 1, 2, 3 places to the left, that could be now written as 12 times 10 to the 3 kilograms, or using a prefix, 12 kilograms. But we're not allowed to double prefix in the SI system. Kilo times a kilo, not allowed. So we could write that as 12 megagrams. That's 10 to the 3 multiplied by 10 to the 3 is 10 to the 6. So the kilo becomes a mega here. Next question, 8,300 kilometers. If we move the decimal point 1, 2, 3 to the left, we could write that as 8.3 times 10 to the 3 kilometers. Again, we could write that as 8.3 kilometers, but we are not allowed to double prefix, so that would be 8.3 megameters. Next question, we've got 1,800,000 kilograms. So move the decimal point from here. 1, 2, 3, 4, 5, 6. We could write that as 1.8 times 10 to the 6 kilograms. This could be written as 1.8 mega kilograms, but again we'll be double prefixing, not allowed to double prefix. So we would write that as 1.8 gigagrams, where the mega 10 to the 6 and the kilo 10 to the 3 can be written as giga 10 to the 9. Always remember though, of course, that the base unit is the kilogram, so we need to be careful of that when we actually use this value in the calculations. Now we've given 0.0056 meters. Now if we move the decimal point 1, 2, 3 to the right, we could actually write that as 5.6 times 10 to the negative 3 meters, or using a prefix, 5.6 millimeters. Next question, 0.000014 meters. If we move the decimal point 1, 2, 3, 4, 5, 6 to the right, that would be 14 times 10 to the negative 6 meters. Inserting a prefix, that will be 14 micrometers. So again, we've inserted prefixes for the numerical values. With this question, a 10 to the negative 3 became the milli, and this question, a 10 to the negative 6 becomes the micro. Let's have a review of the last few questions here, and see if you can rewrite these in a more concise format. The answers are shown on the following slide. Exercise 4 is the solutions. We outlined the solutions to questions Q through to V on the previous slide. Considering question W here, we're given 0.036 kilograms. If we consider moving the decimal point now 1, 2, 3 places to the right, we could write that as 36 multiplied by 10 to the negative 3 kilograms, units of kilograms. So that's in the base unit. But if I want to write it in a more concise format here, we note that the kilo here is 10 to the positive 3. So here the 10 to the negative 3 will cancel with the 10 to the positive 3 to leave us with 36. And this time the unit is the gram. Considering question X here, move the decimal point 1, 2, 3, 4, 5, 6 to the right. We could write this now as 630 times 10 to the negative 6 kilometers. But just notice that 10 to the negative 6 multiplied by kilo, which is 10 to the 3, using laws of indices, simplifies to 10 to the negative 3. So we can write the answer as 630 millimeters. The unit here is the meter. A similar approach is found for question Y here, just that the unit is different. So the answer is 46 milligrams here. For the last question here, question Z, move the decimal point 1, 2, 3 to the right. We can write this as 3.6 times 10 to the negative 3 amps, which is written as 3.6 milliamps. So exercise 4 was simply trying to engage you with the prefixes in how the prefixes can simplify some expressions, how to avoid double prefixing, and just writing numbers into a more concise format. Let's very briefly consider other systems than the SI system. Finally, in overview, I'm just going to very briefly consider other systems of units. This is purely for reference only. This is really beyond the scope of this initial presentation, which is purely focused on the SI system, which is the main system you will see within your college work. But I just wanted to mention to you other systems that you might possibly encounter within vocational practice. In the table below, I've outlined various systems, and there's many more systems than those highlighted here. In this presentation, we've considered the SI system only. And just recapping the base units for length, that's the meter. For mass, that's the kilogram. For time, that's the second. The derived unit of force in the SI system we showed to be the Newton. Now, within my industrial experience, I have encountered what's called the British gravitational system. That's where the base unit of length is the foot, the unit of mass is the slug, and time is the second. The force unit in the British gravitational system would be the pound force, sometimes denoted as lbf for short. At the top of the columns, I've stated the terms of absolute and gravitational, and these relate to the way the two systems are defined. Here are some definitions. For an absolute system, mass is the base unit, and the unit of force is derived from F equals ma. That's Newton's second law of force is equal to mass times acceleration. In a gravitational system, weight is the base unit, and the unit of mass is derived from m equals F divided by A. That's Newton's second law rearranged, so the mass is equal to force divided by the acceleration. So returning to the two systems, SI system and the British system, which you might encounter in practice. On this slide, for the SI system, I've labelled the various base units. So that's the metre, the kilogram and the second. And the SI system, the force unit of the Newton, is a derived unit. Considering the British system, the length unit of the foot is a base unit, the time unit of second is a base unit, and because it's a gravitational system, the force unit of the pound is a base unit. The slug is termed a derived unit. In the SI system, the mass unit is the kilogram. If we want to find the force unit, the Newton, we multiply that by the gravitational acceleration, 9.81 meters per second squared. In the British gravitational system, the mass unit is a slug, and that would have to be multiplied by the acceleration in that system, which is 32.2 feet per second squared, to find the force unit in pounds. From my personal experience, we need to be very careful that we understand the absolute and gravitational context. A colloquial way of thinking about this is, if I ask somebody what their weight is, they may well give it to me in terms of kilograms. And that's used in general parlance. And I've got to know in the SI system to multiply that by gravitational acceleration to find the force, because they've actually given me a mass in kilograms, and I need to multiply it by 9.81 meters per second squared to find the force in newtons. Conversely, if you've been brought up with the British gravitational system and you're asked for your weight, you're most likely to say your weight in terms of pounds. So in general parlance, it's the weight unit that's commonly used. If you want to find the mass, you would have to divide that weight by the appropriate gravitational acceleration to find the mass in terms of slugs. So just trying to illustrate there a practical context of how the absolute and gravitational system's tendency to be used in practice. But in society, the general parlance for weight is either kilograms or pounds. But in the SI system, the kilogram is the mass. In the British gravitational system, the pound is the weight. And that's sometimes where the confusion comes between the absolute and gravitational systems. I have been involved with aero engine work, and I was given weights in terms of pounds. To find the masses, I know I need to divide that by G to find the actual mass of the object. I have also been given weights in terms of kilograms when I'm analysing structures, and in the SI system I need to multiply that by 9.81 meters per second squared to find the weight or the force unit. The other three columns just show you additional systems. There's an imperial foot-pound-second system, which is an absolute system. It has a length unit of the foot, it has the mass unit of the pound, the time unit is a second, and then the force unit is known as the poundal. There are many versions of the metric system. This particular gravitational metric system, the length unit is the centimetre, the mass unit is the slug, the metric slug, and the time unit is the second. The force unit is known as the kilogram force, kgf sometimes. Another metric system, sometimes known as the MKS system, is an absolute system where the length unit is the metre, the mass unit is the kilogram, time is the second, and the force unit is the kilopond. And like I said, there are many, many more systems that you can consider. So within industrial practice, you may come across other systems. You need to be very careful that you fully understand the systems if you're converting units or you're converting masses to weights or weights to masses. And one final definition relates to coherent systems. A system of units of measurement in which derived units are obtained by multiplying or dividing base units without the use of numerical factors are known as coherent systems. For example, if the derived units can be obtained directly from consideration of definitions and formulae. So for example, we know that speed is distance travelled divided by time taken, so v is equal to s divided by t is the equation. If we put the base units into the right hand side of that equation, we will find the units of v. That's a coherent system. Similarly, we can find derived units from laws such as Newton's second law, F equals ma. If we put the units of mass and acceleration into the right hand side of the equation, we will find the unit of force. So the SI system is a coherent system, but not all systems are coherent. You do need to be careful. Some imperial systems, for example, have additional factors that are required to derive certain units. So that would be described as a non-coherent system. So if you are involved with other systems than the SI system, I'm just encouraging you to research that system and make sure you clearly understand whether it's absolute or gravitational, and so how to determine various units in the system. Here's the bibliography used to help generate the presentation, and I hope this has been of interest to you. Thank you for viewing.